Data assimilation. How many times have you heard about this before? Well, honestly, probably not very often, but since its popularity is growing, I thought I would do a short video about it. So, what is data assimilation, or simply DA? Broadly speaking, it is a branch of applied mathematics that strives to forecast evolution of dynamical systems by fusing two things together, data and a model. Without getting into technicalities, a dynamical system is simply something that changes over time, like a hurricane, concentrations of fluids, atmosphere, or planets moving in the solar system. And actually, it might be easier to start by discussing two things that data assimilation is not: machine learning and computer modeling. It's impossible to make a video nowadays without mentioning machine learning, so here we go. Machine learning is often thought of as a system with an input and output, which is treated as a black box, meaning you don't know what lies inside, but would like to infer the internal structure of that thing purely from data. All you care about is the pairs of inputs and outputs, x's and y's. In a classical machine learning scenario, a scientist has only access to raw data and possibly some assumptions about the underlying system. He or she tries to predict the output given an unseen input by observing a number of input-output pairs. For example, suppose you want to predict a car's speed in the future. You only know its current speed. Now, this might seem a little tricky, but if we assume there is some law that describes the car's movements, then by observing it long enough, we might be able to predict the car's speed in the future. Now let's look at what computer modeling does. Here we start with basic assumptions about the underlying system and derive a model that best describes that system according to our assumptions. We then try to approximate that model on a computer, or as we call it, run a numerical simulation. In our previous example with the car, say we know that the person driving the car is Jean-Baptiste Joseph Fourier, so fittingly he would accelerate the car according to a perfect sinusoid. Given initial conditions and Newton's second law, and assuming there is no friction and other idealistic conditions, we could calculate exactly the velocity of that car at any given moment in time. Now, of course, you don't need a computer for such a trivial task, but there are problems that are much harder, like simulating fluids. So, how does data assimilation relate to these two things? It comes into play when you are lucky, or unlucky enough, to have both, data and a model. However, the biggest caveat here is that neither one of them is fully trustworthy. Data is noisy and the model is idealistic. Put differently, your model is somewhat true, the data is also somewhat true, and you want to facilitate a sort of happy marriage between the two. Remember our car example? Let's now suppose we only know that the driver is one of the Fourier family. Joseph's relatives can probably all accelerate a car, but not as precisely as Joseph himself. Let's also suppose that the road is not perfectly straight, it has bumps and potholes, and the car is pretty old, so the engine is acting up, etc., etc. We also have data from the moving car, not only its speed, but also engine revolutions per minute, pressure exerted on a gas pedal, and so forth. The measurements are slightly corrupted by tools that we use to measure those things. You see how it becomes more realistic compared to our idealized setting? It's also more realistic compared to the machine learning case, because really, for many systems we do have a good physical, chemical, biological, you name it, model. Data assimilation originally came from a very practical field, weather prediction. It arose from a need for a hybrid approach that would combine models and data. Weather evolution can be described by a complex set of equations such as Navier-Stokes equations, but due to its chaotic nature and the sheer number of simulations needed, it's entirely impossible to predict weather using models only. That's why models are simplified at the expense of introducing a lot of unknowns, which we would have no way of finding unless we had data. A basic data assimilation algorithm makes a forecast using the model, then uses data to make a correction of the forecast. As time goes by, we observe the difference between our corrected forecast and the true value and adjust accordingly. the biggest challenge is finding the right balance between the model and data. In other words, do you trust your model more than noisy observations at a given moment, or vice versa? There is much more to data assimilation than I've just described. The algorithms get very involved, and some are only guaranteed to work in simple scenarios but are still used to good effect in more complex settings. So, although you may not have heard of data assimilation before, the field has been booming in the last couple of decades and will be ever more useful in the future as humanity learns how to deal with rapidly growing amounts of data. This video is hugely inspired by a YouTube channel, Minute Physics, so all credit for the idea goes to them. I would also like to thank several people without whom this video either would not have been possible at all or would have been of a much lower quality in general. They are listed on the screen. Thank you.